All right, good afternoon. I'm going to finish up our class discussion, and I'm going to put this on YouTube just to answer the questions for Capstone. I like to put all these questions on Capstone because I'm wondering if I like to put them on YouTube. I'm wondering if someday somebody might have these same questions, and I figure why not put it on YouTube. You know, there's actually a verse that says, "Cast your bread upon the waters, for you will find it after many days," in Ecclesiastes. And so sort of, why not? If I'm going to be recording it anyways, let's make it public and let's answer the questions. Now, I'm not going to do much preparation for this. This is just like it was in class if we had a little extra time. Okay, so let's finish it up. Can we predict that future evolutionary changes, how far can we go to selectively influence evolution? And this is partially contained in the paper. There's the experimental evolution of where you can go and what kind of questions you can ask. And actually, I want to point out that Thomas had a good experiment for how things would change when you change the soil and change the elements that are there. And so there's a question of how far can you go? The one thing I want to reiterate, the same thing I said with the paper, fitness is not really the same kind of mathematical thing as a direct measurement of spatial extent or time extent or things like that. Fitness is a relationship. It is not a isolatable mathematical quantity. It's how the organism fits into its environment. It's contained in the measure. So the question of how far can you go to selectively influence evolution sort of depends on how you define fitness. How far can, and in fact, a little bit of suboptimal fitness might actually cause novelty to emerge. Because if you're perfectly adapted and perfectly fit to your environment, you won't ever change. You'll have something probably like the coelacanth. And so it's really interesting to think about how evolution is not really this mathematically maximizable function. It's a good enough kind of thing. And so how far can we go to selectively influence evolution? I would say that this is determining where those bounds are. You know, you want to be alive. You have to be alive to continue for life to evolve. But also, if it's perfectly fit, it also won't evolve. And so there's actually an in-between. This is sort of the message of the whole book. There's constraints and then there's freedoms in all these systems at multiple levels. And there are some levels, like the genetic level, that has more freedom. The junk DNA that happens is probably a result of the freedom that the DNA has. And don't take this as a DNA has all the freedom, therefore it's all junk. You know, or DNA is constrained, therefore it's all not junk, you know. It's actually probably somewhere in between. And the fun part is we get to talk about it and we get to think about it, about how we can do it. The amazing thing is that we can selectively influence evolution. We can work within some bounds, but there are going to be trade-offs that will constrain what we can do. So we talked about this, but I do want to point out this is one of the big themes of the book. One of the things about chemistry is it is more constrained than, say, genetic sequences. Genetic sequences give you a measure of, basically it's like blank pages that you can write on. And those also are constrained in some ways. They're just less constrained. You can have a lot of different genetic sequences that will solve the same functional problem. And so the universe is not all about function. In fact, it's about some of the transcendental qualities like truth, beauty, and goodness. But I'll let you think about that for other classes. Just, have fun thinking about the big questions. And this is sort of a similar but more focused question at the bottom. If beryllium and strontium were more abundant, could they have replaced calcium's role? And I think they certainly could have. In fact, beryllium maybe not because it's so small. Strontium, I almost wonder if it's abundant enough to actually replace its role in some actual places. And there's actually a science story, I was just reminded of it, by Isaac Asimov about a planet that they go to that had a lot of beryllium in it. And it was about them, I even forget whether it was a good thing or a bad thing that it was beryllium-based life, but it was like a beryllium-rich planet. and they went to, and everything was the same except beryllium was there. Now remember, beryllium and strontium are going to have different sizes, and that's an important part of how the element fits into its area. So you'd have to have everything else adjusting too. So the question is not, can we go to beryllium-rich planet and live there? There'd probably be problems. I think that was Isaac Asimov's story. It was specifically beryllium, if I remember correctly. But the other thing is, could there be a strontium dependent? Just like we have nitrogenases that are dependent on different metals. We have iron ones, we have vanadium ones, and so I don't see why not, except, I mean, could there be an environment that was rich enough and did not have calcium? That's the other thing. If life already uses calcium, it's already optimized for that. Even if strontium could substitute, life doesn't have an incentive to move towards strontium if calcium is working just fine. So it'd have to be like a monolake type situation where not only are you rich in the one thing, in the new thing, you are poor in the other element. And in the case of monolake, it didn't work for DNA, right? But for cell signaling, I don't know. Maybe strontium could replace calcium in some places. It would take a lot. I would not put my money on it, but I think it would be fascinating to investigate. And it might be investigatable by genomic means, which means more practically you could search through tons of genomes for evidence of this. So during the Cambrian period, why did life accept elements like phosphorus and molybdenum but eject the extra calcium? This goes back to actually chapter 2. And I was thinking about bringing this back every chapter because it does really shape every chapter. It's the figure where you have the cell and you have the things that are in and the things that are out. This is actually those same rules, and they apply to every chapter, including number 9. And so the phosphorus and molybdenum are in different roles, and so it's going back to that chapter 2 thing. You always have to eject calcium, and in fact that goes with an old experiment where they were first starting to work with recombinant DNA and things like that. They needed to make the DNA solid. The way to make DNA solid is to add calcium. It turns into a snow-like precipitate, and then you can isolate it, and then you have a bunch of DNA that you can work with biochemically. And so that just shows you, if you add enough calcium, DNA precipitates, and once it's precipitating, it's useful for scientists, but it's not useful for life. So I like to remind you of that, and I want to remind you of that everywhere. And those rules have a chemical logic that applies universally. So it's not just about chapter 2 and chapter 9. It's also about other planets that are water-based, similar temperature range perhaps. If they're like Earth, these rules would apply to those planets as well. And that's the real strength of looking at things from a chemical perspective, in my view. Could oxygen availability be used as a predictive tool for identifying when other planets might experience an explosion in biological complexity? Well, certainly it is probably the thing that you might see in the news someday is that they detect oxygen, a signal of oxygen in a planet. They just did this for dimethyl sulfide for a planet. They're using spectroscopy to look at other planets' atmospheres. And these are outside the solar system because we can see the ones in our solar system already. But now that we can actually have telescopes that can find other planets, they can actually do spectroscopy on those atmospheres. And be very careful about this. People have been wrong about this area before. But they just had a news report that looks more solid than the other ones, that they found dimethyl sulfide, which is a metastable compound. It's not stable enough to form just by itself. And so it will actually, it should react if there's only geology going along, unless there's biology that's making metastable things. Biology is by definition away from equilibrium. And so you don't see dimethyl sulfide under any known equilibrium conditions. So they found it. It's not the strongest thing, and the thing that I would look for would be oxygen. Oxygen would be metastable. So metastable things like oxygen and dimethyl sulfide, I think that you could use oxygen availability as an idea for not only where the planet is, if this other planet with dimethyl sulfide is actually life containing, then it would be predicted to not be past the great oxygen explosion. It would be predicted to be before that, at an earlier stage. And so the answer to this is definitely yes. Right now, we are only able to detect or not detect. We're not able to really quantify. But if the technology advances enough, maybe we could quantify. And maybe we could say oxygen's at 10%. Oh, this planet's just about to have its Cambrian explosion. It'll probably be too far away for us to get there because these things are hundreds of light years away at least. Although the planet that we found with dimethyl sulfide was surprisingly close. I think it was only like 100 light years away. Anyways, we can look that up. News will continue. But oxygen is exactly what extraplanetary scientists are looking for in the atmosphere of those. And it would be a huge sign of life. Still, there'd be some people who would say maybe it could be geologically made rather than biologically made. But it seems unlikely until we have the mechanism for that. I would actually be skeptical. If we detect oxygen, I think that we could say that's pretty strong evidence of life on other planets. And this is another question about oxygen. Oxygen is taught about as being low in energy because it has a delta H in chem. But we learn that's not the case. Why is O2 used as baseline? Well, it's low in energy in only the sense relative to, you have to always say, what's it low in energy relative to? And actually I have a whole paper about why is fire hot, is what I call it. It's why our combustion is always exothermic. If you look at that paper, and you look at all the other things in the main reactions, it looks at all the combustion reactions that we can even think of that involve carbon, oxygen, nitrogen, hydrogen. And on that table, oxygen is way up here. So as far as stability goes, you've got to always define your reaction. Oxygen is up here in that paper, and so oxygen is actually less stable than the other things that react. And that's why when you react it, you actually end up getting something. That's why I call it metastable, because it will easily fall back down. CO2 is a lot lower in enthalpy than oxygen is. Now, heats of formation will show oxygen as O2 because oxygen O2 is more stable than 2O, okay? But it's very important. That's not a physiologically relevant equation. That's more for calculations and things like that. So oxygen is actually, in a sense, high in energy. And that's exactly the message of the entire the paper about why is fire hot. And just remember, I can show you the graph. Oxygen is actually relatively high in energy relative to other reactants in combustion. Always look at it relative to that. And so the thing about being higher or lower in energy, also be careful about how you talk about those things. Delta H for what reaction, low in energy in what sense relative to what. These are numbers, and we have to define our states. If we're saying a delta, we have to talk about what is changing from to, what is changing to. So you have the initial and final states inherent in the delta. So be very precise about what you mean by being low in energy. And the oxygen is not really described as being low in energy in my book. In fact, it gives the energy to the processes. So be very careful about these terms. And so the final question is, if a large deposit of a semi-rare element worked its way into the ecosystem, would that ecosystem grow dependent on the element and die off if it ran out? How long does it take an ecosystem to grow dependent on an element? And this is a very interesting question. I would look at the kinds of enzymes where we have multiple metals for different things. It seems like this is a plausible mechanism. I don't know if it's ever actually been really proved. And so there could be a good investigation here looking at this from an experimental evolution sort of standpoint. I don't believe that Richard Linsky, the one with the long-term evolution experiment that was mentioned on the previous slide, I don't believe that he ever actually talked about doing something like this. He was always just working about maximizing in one step. But what if you maximize in one step and then take that thing away? It's a logical next step, but I don't think anybody's done it. The key thing would be, could it go back easily? And in many cases, there are sort of backup copies of genes, and there are sort of fuzzy margins to whether things will. Most things are not crucial to the survival of the organism, and then the organism can just move. I think plants would be probably the best way to look at this because they can't move. Soil elements would be the way to look at this, not animals. And actually, this would be a question for Tim Nelson if somebody has a good experiment that shows this. It's very logical, but you need to have something that is so important. There's lots of things that are important to an organism. To have one thing where you take it away and it dies. Well, organisms wouldn't survive long, and they've survived a long time. They wouldn't survive long if they were like that on many things. So it'd be interesting to see. Usually new elements are toxins and not used. And so it's the question of, could the floor fall out from under an organism? Probably yes, but it would take a specially necessary element for that to happen. More likely, you have something that's toxic at first and it adapts to that, but then if that thing goes away, then it can just go back to the old chemistry that it used. Nitrogenases would be the one that I would look at. They're the ones that seem to use different metals the most. And it's interesting to think about that. But we also don't know exactly how they work, exactly how the different metals work, or even necessarily the sequence. I think that the sequence I have in the book might have been modified by a few papers since it. So it's a big question. And that's what I want to think about and I want to leave you with. So thank you for these questions. Think about them, and I will see you not in class on Tuesday because we will have an online seminar that I want you to go to, but instead I will see you on Thursday for our first round of Presentation 3.